We are looking at regularization and validation as two different ways to try to solve overfitting, and then to understand different ways of doing validation, and then show how validation and regularization complement each other. Okay, so just to be clear about what's going on, basically what we're trying to do is get a good handle on this particular thing, which is our J test, right? This is our out of sample, which they call it, okay? But basically the test error, right? So when we get new data coming from the problem, okay, so we have new data after the classifier has been trained, how do we ensure that the error doesn't go out of whack, right? So we need a model that's trained well, and it needs to be trained in such a way that it generalizes to new data. It's not capturing specific regularities within just the training data, right? So we do that by making sure that we don't have an overfit of this. Okay, oh, you can't see the screen. Okay, thank you for telling me again, so I can make sure that it's there. Okay. All right, so hopefully the screen sharing is back. Thanks for telling me about that. I do depend on you to make sure I'm not making a lot of technical errors. Okay, so I'm gonna just make sure I can see the chat because yeah, there are too many screens in Zoom. Okay, yeah, thank you. So again, we have these two things, right? We have, this is what we really care about. This is what a contractor or a company will ask you to do, is build a classifier that has less than X amount of error, right? And you can't guarantee that. The best that you can guarantee is that your training error is under a certain amount, okay? Actually, we can guarantee that within statistical regularity. Unfortunately, we're not going to go through all of those parts, okay? It has to do with how tight a bound you want and how many samples that you can dictate, okay? How many samples you need to make sure that the bound is tight, okay? But, you know, even though we have a certain amount of training error, we also have to cater for the fact that we might be overfitting, right? Our hypothesis might be, you know, basically capturing more than is warranted, okay? More than just the data, but sorry, more than just the signal of the function, but also data that includes all of the noise, right? Both the deterministic noise as well as the stochastic noise. So the first thing we're going to do is look at regularization. Regularization says that we are going to look at the overfitting penalty, right? So the overfit penalty basically says, you know, I'm looking at this hypothesis, it somehow doesn't seem to match very well, okay, because it's like capturing very specific. So I'm going to try to restrain the model to only look at things that I think are, you know, relevant things, okay? So in the case of concept learning, again, when we talked about capturing what type of drinks you or your friend would like, we said that, you know, a conjunctive learner sort of makes sense. And we also showed that there are some cases in which a conjunctive learner wouldn't work, okay? But, you know, having a model that can learn everything also is not feasible, right? You can't learn anything from that. So the overfit penalty is basically trying to capture, okay, did you pick a hypothesis set that sort of makes sense, okay? So we're going to start with that first, right? So what we want to do is constrain the model, right? We want to go back and say, you know, the model that we have, maybe we can say, maybe we're just not going to let it fit the noise, okay? And that sounds wonderful, okay? Because what we want to do is get rid of all of these wild lines that are coming here, right? If I set the regularization on, basically I'm saying that somehow wild parameter values cannot occur, okay? I'm just going to blast them out of the picture. So for example, here you can see that the slope of some of these lines are pretty far away from the norm, right? So that corresponds to our H1 coefficient, right? Our slope. So we could just say, you know, don't allow things that are too big, okay, because we expect all of the function values not to depend too much on one particular function, one particular feature. So we're going to constrain that, and we'll get something that looks like this, right? We're going to constrain the weights to be, you know, a bit more reasonable, so that we don't get those wild curves that you see on the bias variance lecture. Okay, so of course, when we do constraints on our weights, that means we're, you know, not allowing all possible hypotheses to encode, right? Sort of like the idea of using conjunctive hypothesis, right? We said, well, you know, it doesn't make sense to have disjunctive hypotheses. We're only going to allow conjunctive hypotheses. That's going to constrain us a bit. So our bias is going to come up because the error due to our representation, what happens if your friend actually likes things different on different days, or with ice, or a different drink without ice, we can't capture that anymore. Okay, so basically our bias error is going to go up a little bit, and you can see that makes the variance go down quite a lot, because we basically said, you know, all these wild areas here, this big fat area of gray, we're tossing those out. Okay, so we'll get a little bit of increase in our bias, but we should have lowered our variance substantially. Okay, so if you think about this, it's actually really true. We can think about H1, H2, you know, with X coefficient and X2 coefficient, like X squared, okay? It's already constrained, right? Basically, our theta 3, theta 4, theta 5, all the way to theta 10, in an H10 model is all set to 0, right? So then our H10 class is actually the same as the H2 class, just that we turned off certain coefficients, right? So in some ways, we are already doing some constraining when we move back from H10. We say H2 is a better fit than H10, okay? That only means that we've just turned off some weights, right? So we can see that H2 somehow is a proper subset of H10 already, okay? So what we want to do, instead of making a hard constraint, is find another way to set the constraints, okay? Because we don't want to be that draconian and say, you know, you must be set to 0 for us to use this parameter, okay? So what we're going to do is to say something like what we did in the SVM. We're going to use a budget, okay? So I'm going to give you a budget of a scalar budget, and you're allowed to spend that budget on any coefficient, okay? But once you spend that budget, it's gone. You know, you can't use it for another coefficient, okay? So that's the idea, okay? So we're going to use the same thing that we saw in SVMs, okay? Basically to set a budget, and then with that budget, let the learning algorithm decide what to use, okay? So that's what it says here, okay? I give some budget number, C, okay, whatever that physical budget is, and I say, you can spend it on whatever parameters you want for the problem in linear logistic regression, but make sure the sum of all of the coefficients is not greater than C, okay? Can be equal, but not greater, okay? So that's the whole idea, all right? So now we have this nice case where basically we have variable, right? So we can do anything in between, right? We can make H1 smaller or bigger, but we're just saying that the C is picking how much budget that we have a constraint. So as we get larger and larger budgets, it becomes more like an expanded universe of hypotheses. When we shrink the budget C, we're getting much more constrained weights, right? They are going to tend closer to 0. All of the squares are not going to be allowed to be too big, okay? And that's the whole idea, right? And actually, this is very nice because we can get this type of thing almost for free. So if you remember the normal equation for linear regression, which is on the left-hand side here, right? We saw that basically what we wanted to do was solve this constraint, solve this problem in a closed form for squared error between the classifier's output and the actual answer. And what we're going to do is try to make sure that we can satisfy that. So we want to minimize the training error. And then we saw there's a closed form solution involving the pseudo inverse times the actual class label. Okay, so we can solve this. It takes a matrix inverse operation that's order n cubed. But if we don't want to do that, that's fine. We can use stochastic gradient descent, which is what many people end up doing anyways for large data sets. And we can solve this approximately. Okay, so the only difference between using this formula in the case where we have a regularization budget is that we're just saying, oh, you know, these thetas, they have to be within a certain limit. You know, the square of the weights, so this is just the square, right? Just written in a linear algebra form. Okay, so you take the dot product of the vector times itself, has to be within a certain budget, right? And so how we do that is just being able to complete the algebra for that, which we'll see later on. And then we will be able to do this, okay? So I will go over that in the post part of the lecture, all right? So once we have this extra term on the side, so we are already having the minimizing of the training error, and then we're now saying we have a regularization parameter, okay? That regularization parameter is going to say, what constraints do I have on this red part, okay? How big am I allowed to take it, okay? And so what we are going to do is take that budget C and then divide it through in some ways by the amount of data points that I have, okay? And then I can see what it does, okay? So you can see here with lambda equals 0, again, if we have this 10th order polynomial to approximate a 5th order thing, okay, we will get bad results, all right? So you see the target function, even though it's a lower order, we get overfitting, okay? And we only need to introduce a slight amount of regularization that's going to penalize large weights, okay? And then we already get a very, very good fit, okay? So we just introduce a tiny bit of this medicine, regularization medicine, and then we're going to get a curve that's not so wild like that, okay? So it only takes a little bit. As we increase the amount of medicine that we're giving, okay, increase the amount of regularization, our parameters are going to grow smaller and smaller, okay, and then it's going to tend towards underfitting, right? So you can see it here. The underfit gets worse and worse because the type of slope that we get in our classifier is going to wean off, right? If we turn on regularization very high, basically we're allowing none of the weights to be anything but 0, okay? So if we have everything is a 0, I think you know what the answer to that classifier looks like. In this case of a 2-dimensional classifier, it has 0 slope, 0 intercept, so it'll be a flat horizontal line on the x-axis, okay? Everyone clear about that? So that's the idea of regularization, is to say that, you know, those wild things that we saw in the bias variance part, we're going to disallow them. We're just going to make sure that the parameters that I allow our optimization to set are not too big, that they're somehow constrained in some way. Okay, so that's the first way. So that's the more tricky mathematical definition for that. So if you don't like the math so much, then you can always appeal to validation, which is much, much easier to understand. Okay, so validation is the other part where we're going to check how well we're doing by actually getting a chance to know what J test is, right? Our out of sample or test error, okay? So we're going to figure out what this is by hiding some of our training data from the training, okay? So you've heard about this probably already as you're starting to do your projects, okay? So how do we actually do that? That's very simple, okay? So we are thinking about deriving it mathematically first. So we are thinking of looking at a test point, okay? We know what the cost of the test point is, right? It's just, okay, the mismatch between the hypothesis, our best hypothesis output, and the actual true class, right? So this is a point-wise estimate. That's why it's lowercase j. And we have different ways of assessing that. But basically, again, as some of you are now quite comfortable with, it's the expectation of that particular test point, okay? So, you know, some of our test cases are more common than others. So we expect to see those types of instances more often. So they will, of course, express themselves more in the expected test error. Okay, so we're going to understand that over the entire testing data set. Okay. So what happens when we look at a single test point? So this is our error, this is our expected value. And then if we look at the variance according to the test data, of course, we can't select the actual data that we get. So we're going to have a noise value here, right? It's a sigma squared based on the samples that we get. Okay, so what we want to know is how well does the test validation, our test performance depend on the size of the data set. So we were looking at a point just now, and our point error says basically our validation cost is going to be sigma squared, okay? Sigma squared. Okay, so if we use more than one point, maybe we can get the variance of the test error to go down, right? We want that to happen because basically we want a more accurate estimation of how bad our test error is. So instead of using 1 point, let's use 2 points, or better yet, let's use a set of points, okay? So we're gonna say, we're gonna choose a set of points from our data, okay, from our training data. We're just gonna take them out, okay? We're gonna call them pseudo test data. So we're gonna take the big pie of training data, cut off a small portion and say that is called our validation set, okay? And this set has K points. Instead of just having 1 point, we're going to use K because we know we can lower the variance of our test estimated error when we have more than 1 point, okay? So how much better does it get when I have a set of points, okay? Well, that's easy, right? I already have the point-wise error. Okay, that's this lowercase j. So I'm just going to average the error over all of the individual point errors, right? I can calculate this exactly because this is on our held out validation set. It's the set of the training data that we locked off on the side. We actually have the answers to. We could have used them for training, but we didn't. We used them as a pseudo test set. So it's like, for example, you go, let's say you're studying for A levels or something like that. You go by a 10-year series, you take all of those exams, that is your validation set, okay? So using that validation set of the 10-year series, you can get some idea of how well you're doing, right? That's why we take mock exams anyways, okay? So how much better is it, okay? So what we can see is that the expectation hasn't changed at all, okay? Because, well, it's just an average over all of the test points that you have, but our validation has changed, okay? Our validation has changed because there are lots of cross terms, okay, that all go to 0 when we are doing that, okay? So basically we have this type of validation error, okay, as we saw on the first point. And so we are actually not just taking the average, but because we have 2 sets of variables, right, a point and another point here, we are going to get a matrix of correlation terms as well. So those all correlation terms are 0 because they're all independent of each other. So we get a savings, okay? 1 factor of 1 over k goes away, and then we're left with this, okay? So this means that as we add more data points, our validation error, a variance of our validation error goes down. So we're getting better approximations, okay? So it also tells you that the amount of validation error scales with the square root of the number of validation points. So it's important to have a set of points, but it doesn't need to be too big, okay? Because the bigger you make it, the less power the square root has in helping to reduce the amount of variance. Okay, so again, I was saying that because we have the sigma square term for 1 point, when we have k points, it's going to be divided by k because we have k points. But because the variance is dependent on 2 cross terms, right? So the 2 cross terms, basically their cross terms will all be 0. So we only have the diagonal that's responsible for the variance. So that means another factor of k will be canceled out. And so the variance estimation will actually get better as we enlarge our set, right? So it's important to have enough points for variance lowering when we establish our validation set, but having a lot of points doesn't help because again, you can see here, by this square root. You know, a larger number of points will only increase by a square root factor the confidence on our validation error variance. Okay, so like I said already, we take the data set, we take k points out for validation, and we save the rest of the points that we have for training, right? And we want to use everything for training. And you've already seen that if we have only 1 point, we get a bad estimate because our variance is sigma squared. But when we have a large K, then we can get something like that, okay? So here, you actually get a better result for a larger K, but it won't get that much better because it tails off with this square root. Okay, so we can do this several times, okay? So we can decide how to take our training data and our validation data to come up with a validation cost. And this validation cost is basically our estimate of our test score, okay? So just to be clear, this H minus is the case. Why we do it minus is because this H isn't over our entire data set, right? We are only taking it on the training data that we saved for actually training the classifier. It's not all of the M points, it's the M minus K points that we have, okay? So that's going to estimate our J test. Now, actually, when we want to put our classifier into production, we never want to use a H minus. We want to use all of the data to make the best possible classifier. So we're going to use all of the data points, not just the training data, but the training plus validation together to create our actual classifier. And so our estimate of the cost of the test costs will be slightly off, right? Because actually we don't have that, right? We are estimating on slivers of the data, okay? So one rule of thumb is to use a K that is 1/5 of the data. You can use 1/10 if you have a lot of data because maybe that's effective enough. Like I said, if you have a lot of data points, the use of validation will tail off. Okay, let me try again. So it will tail off as the square root of the size of the validation data. Okay, everyone good with that? I'm sorry, the internet is really flaking out. And if you understand what I'm saying, please give me a thumbs up or a yes or no, and then we can go on a little further. Anyone there? You guys able to see? Okay, thanks Felicia, thanks Kathy, thanks Sudarsono. Okay, so hopefully you understand what the validation is doing. Okay, so we come to the key part of the lecture at this part, which is the cleanliness of validation, which people are usually confused about. Okay, so what's going on here? We are using some of the training data to get a handle on the estimated test error, okay? But when we use the validation to tell us what thing to do, we are actually using it to make a choice, okay? So for example, in the first part of this lecture, we said we are going to set regularization, and we showed you this chart, which illustrates how badly or how good regularization has an effect on our validation error, okay? So we're going to pick whatever validation amount seems the best for the data set that we have, okay? So out of these pictures, it's clear that, you know, a lambda 0.00001 is the best because the red and the blue curves look right on top of it, okay? But we made that choice based on how well the classifier performed and how well the classifier performed on our validation data set, okay? So that means it's not actually performing as a test set anymore, okay? It's a validation set because we made a decision based on that, okay? So when we use the actual test set, that test set is unbiased. We have no knowledge about it. We can't use it to set any decisions, okay? But when we use a validation data set, then we have some problems, okay? So we're going to ask ourselves, does the validation set have an optimistic or pessimistic bias? So let's explain what we mean by that, okay? Let's say we have two hypotheses, okay, for a data set, okay? And their actual test error, okay? The actual error on our test set is the same, 50%, okay? So it actually doesn't matter whether we choose H1 or H2, okay? Now, when we use validation, okay, and we use validation to pick H1, okay, by training on some part of the data, okay, and we use another part of the data to pick H2, to engineer H2, we are going to pick one of these guys, okay? Which one am I going to pick, all right? Well, I'm going to pick it easily by basing it on its error, right? The error, whichever of these error values is lower, is the classifier value or the parameter value or the regularization value, whatever. Any parameters that I want to set can be best optimized by picking the classifier with minimal error, right? Okay, so when I try to estimate this, okay, this means that I will normally have a case where my expected error is going to be less than the actual error, okay? And that means I'll get an optimistic bias, okay? So that's pretty confusing, so let's deconstruct it, okay? So here's a case of, let's say, these two different classifiers, H1 and H2. They're exposed to different parts of our data set. They come up with their own classifiers. And then I'm going to use validation to find out the approximate test error. It's our validation error, okay? Now, H1, when it's optimized, yields a performance that has less than 0.5 error. It just happens to be that way, okay? In this particular example, okay? And then sometimes we'll get, just because of the pick of points, some errors on some points or some slabs of our training data that have higher than that average error, okay? So you can think the true test error is 0.5, okay? But depending on which data set I actually get exposed to, I might get an error that's somehow slightly better or slightly worse, okay? So the problem here is that we're actually going to pick one of these. We're going to pick H1 or H2 based on the cost, right? The cost on our validation, okay? Obviously, we want to pick the minimum, okay? So if we have, let's say, 10 or 20 different H's to pick, we're going to pick the best H, okay? When I pick the best H, I'm discarding the other ones, okay? And that means that it could be that those optimization is actually good in general, but it could also mean that it's just lucky, right? I get a good pick, all right? And I get an optimistic estimate of my test, my actual test error. Okay, so you can think about this as all things being equal, I'm taking draws from a random distribution, okay, a Gaussian distribution, sorry. And, you know, if I'm using that Gaussian distribution centered at 0.5 to pick a hypothesis, I will pick the one with minimal error, and that's going to lead me to an optimistic bias. Because again, I'm using the actual test error, the validation error on these two hypotheses to decide, okay, to decide the set of parameters that I'm going to apply, okay? So that's why it's an optimistic bias, okay? Does everyone follow that? Okay, so again, if you are not clear about this, please let me know on chat, or let me know in the yes and no. Okay, so Qinghan is clear about that. Li Shuo is clear about that. Felicia, Hanzeng, Kathy, Mirabelle, Paul, are you guys okay or not clear? It's fine if you're not clear, okay? I can explain it again. This is something that I think the video is not very clear about. And even if it's clear to you in the videos, when you rewatch them, some people often have a lot of questions about this. Okay, so I take it that you guys are all fine. So we'll go on from there. Okay, so yeah, so you understand validation. So once you do validation, why don't you do it more than once, right? So we could use validation to pick the level of regularization that I'm going to use. Okay, but I can use it to also pick models, all right? So in your projects, you know, I said maybe you can have different people responsible for different classifiers. So somebody can run an SVM, somebody can run naive Bayes, okay? And you guys should all specialize and learn a little bit more about how those classifiers work, okay? But ultimately, you are going to perform the best possible you can on the project, right? So why use a naive Bayes solution if it doesn't do so well? Maybe I can use an SVM one, okay? So the final one that you pick is also going to be something like validation, right? I can say, I've got different hypotheses, okay, coming from different learners, which may have different parameters. And I'm going to do validation, right? I'm going to use validation and use each of the different learners to come up with its own hypothesis, and then look at the hypothesis output, okay? It could be the same learner with different parameters, or it could be different learners, class entirely, okay? And we're just going to look at their performance on our validation cost and then determine which one I'm going to pick, okay? And then I say we've chosen this particular classifier because it does the best on our validation error. And you can see right here, this is the uh-oh part, right? Because we picked the model with it. It's not a bad thing, okay? But it does mean that our validation error is going to be generally better than our test error, right? Because we have picked the classifier with the best validation error, okay? But we don't know how that's going to generalize to the test data. Okay, so in terms of ideas about how contaminated the error is in getting an idea of the actual thing that we care about, performance on out of sample or test data, right? We know that training data is hopeless, right? Because we use that to train the classifier, okay? Validation error is better because we don't use it to train the classifier, but we use it to set some additional decisions, okay? So we don't use the data points to train, but we use the data points to decide regularization parameters, or what we call generally hyperparameters, parameters that govern how the learner works without fiddling with the. Okay, so we are done with this set here. Just hopefully you understand what's going on. We have basically these two curves, right? One that is our validation error and another one that is our test error, okay? And you can guess which one is which. We've already said that the test error is in fact usually higher, right? So that gives the answer right away, okay? So I hope you can answer these questions to yourself. If you're adventurous, please put your answers on chat, or if you want to check your results. Okay, let me try to share the screen again. Okay, and why are the curves going up? And why do the curves get closer together, right? So when I change the validation set size to a larger number, why do these two curves get closer together? Okay, so I'll pause there for a second. And, you know, because we have such a small group today, I encourage you to unmute or post your answer on chat, and then we can discuss that a little bit. Okay, so that's the end of the pre-lecture session. So we are going to spend a little bit of time talking about the questions that you guys have, but also the post-lecture as well. Okay, so we actually talked about this one. So I'm going to see whether, yeah, I can. All the IT stuff is not working for me very well this week. Part, which is our post lecture. Okay, let's make this bigger, sorry. all right? So when we want to solve for regularization, what we want to do is, again, think about how to set this constraint, okay? So the way we can think about it is really simple, all right? We've got, let's say, a case where we have two parameters. So these are not our x values, okay? These are our parameter values. So I have a bias term, theta 0, and a slope term, theta 1, okay? And basically, this maps out a two-dimensional space of all possible settings for an H1 classifier, right? So H1 has theta 0 and theta 1, okay? And I'm showing you a heat map. That heat map is basically, the more red it is, the less the error on that classifier is our training error, okay? So when we train the classifier, we want to have a minimal amount of error. So you can see where we're going, right? What we want to end up with is a point somewhere around here, right? So yeah, somewhere around here is the best point that I can get, okay? So when I solve this equation exactly, I'm going to end up going there. Or if I use gradient descent, right, maybe it starts with a set of parameters just like this one, it'll gradually take steps towards that point, right? So now let's interpret what we mean by having some constraints, okay? So I'm saying I don't want to set this particular set of values to exceed some budget, okay? And so what our budget looks like is a little bit different than this, right? So let's go back. Okay, our budget ends up looking a little bit like this, right? Because we have a term and we're taking a square of all of the different values. So it ends up being concentric circles, right? The concentric circles are around the origin, right? So if we had no budget at all, our theta 0 and theta 1 would be 0, right? We'd be sitting at the origin, okay? If we are allowed some budget, then we can set our theta 0 and theta 1 to be a different value, okay? But still sort of close to 0. So we're basically going to say that it defines some type of polygon here. We're just making it a circle, right? And then what we already saw is on the heat map, basically, what we're saying is that any pixel on this heat map that is the same color basically says that our training error is a constant value. Okay, so we can walk all around the oval of this training error without descending or increasing our training error. Okay, so in the normal optimization process, we want to get to our linear solution for regression or whatever, you know, any algorithm that we have to find a good solution. Okay, and so what we want to do is find a solution that is constrained by our budget, right? So as we increase our budget, let's say our budget is C, okay? And so I'm gonna plot the circle that signifies the solution to this where it's 0, right? So where the square of the norm of the matrix, the parameter vectors is the same as C, okay? So this is going to give me a circle. Okay, and if that circle does not actually hit our our normal linear regression solution, I'm going to try to find the one that gets the minimal solution. So it's going to be somehow tangent to the solution. Okay, so you know, basically what I want is to find this point here. Okay, and then you can see what this happens is that the surface of these two things, right? Our circle that defines the budget for regularization and some type of surface or polygon for the same cost for our test cases, okay? They're going to meet, they're going to intersect at some tangent. And we can see that the surface here is perpendicular normal, right? Because I could pick another point, let's say this point over here, but this isn't a very good solution because if I just keep on walking on this budget and I get closer and closer in this direction, I'm going to minimize, I'm going to further lower my training error. So the place that I'm going to put my point is, of course, the one that's perpendicular in both directions. It's going to be perpendicular to the solution, to the origin of where this circle meets this ellipse, okay? So, we have this solution. So as I increase my regularization, this circle shrinks, okay? And the lambda goes down, okay? So yeah, sorry, when my budget goes up, that means I have a larger circle, not a smaller one, I misspoke. And that means, yeah, let me just double check that I've done everything. Yeah, so lambda is the same as C, okay? It's just another way of thinking of C. It's normalized for a bunch of points, right? So we're doing it on a per point basis instead of a C basis, okay? So usually we think of setting an amount of regularization based on the average amount of medicine that we want to take for each individual point, right? So it's an average over many points. Okay, but the C budget that we introduced before, it's an absolute value, so it doesn't scale to the data set size. This is why we change it from C down to a lambda value. Okay, so we shouldn't have less regularization when we have a big a big amount of data, right? It should be according to the size of the data set, the average dose of medicine for a point. So I hope that answers your question. Okay, so earlier I alluded to this fact that when we are trying to solve for a regularization solution, a closed form solution, like we did with the pseudo inverse for linear regression, actually we can do it. It's not particularly hard, okay? We have this constraint. We want to make sure that the weights of these lambdas don't exceed a certain value, okay? So here we're using C instead of M because we don't want any dependence on our M, okay? So we're just going to stick with this constant for those purposes of the proof, okay? And so this is actually fairly simple. We just have this constraint here that we have, okay? So we are going to make this an equivalence, right? So we now introduce our lambda and M, okay? And then you can compare what happens, right? So I'm just going to carry out this cross term, right? So I have the multiplication of our two parts for this, and I have the constraint here, okay? So now I'm not saying that I have a specific constraint, okay? I have an implicit constraint because all I want to do is minimize, okay? I'm not gonna say that it's subject to an inequality constraint because that's hard to engineer. I'm just gonna say that I'm just going to add to my training error this regularization penalty, okay? This, overfit penalty, if you will, okay? So I want to minimize this square as well, okay? So if I take the derivatives of both sides, because again, when I take the derivatives, I can find the minimum, I can find the stationary saddle point, right? Then I can do that. And you'll see it comes out fairly nicely, okay? I take the I do the multiplication, right? Because I have the x is here, it's a square, then I would have the multiplication of that through. The other terms don't have an x, so the only dependence is on theta because we're looking at to minimize the error with respect to theta, right? So then I'm going to get the same thing as before. It's just that I have this particular point here, okay? This is going to just be this part that's inside, right? And so I'll just have this one part here, which is the identity matrix, basically having a diagonal matrix with ones all the way down the side for all of the thetas, okay? And then I can just plug it in. So actually it's very, very clean, okay? All I need to do is figure out what amount of regularization I point in, and then I can still use a version of the normal equation as we had introduced in the linear lecture, right? So I just have this extra term and I can still solve for that, okay? So that's very nice. It means that if we want to add this idea of minimizing the set of weights subject to regularization budget, I can still solve this in one step. Okay. So let's go on to regularization variance. So in regularization, variance is also very simple. Okay, so we had talked about this part over here where we're saying we're going to take the square of the weights, sum them together, and that is our budget. Okay, so we can think of some function, let's call it omega of h, that is going to characterize what we're going to optimize against, right? We were trying to minimize that, okay? So when we do this, this is called uniform weight decay, okay? And we'll come back to that in neural networks. It's not a big deal, okay? It basically says, again, we don't want wild values of parameters, large ones, because they're going to have all that wavy line stuff, okay? So we don't want that. We want very smooth things where we set, sort of like normal weights, not too high. It's okay if they're low, to make sure things get together and they don't have these wild curves, okay? Now you might ask yourself, well, it could be that some of the features are engineered so that they fit really well, so you should be having a very high weight for those particular features and a very low weight elsewhere. Maybe if we set something inversely, okay, we want to say, we want something that is very high, okay? So we want to have all of the weights that are high for larger parameters should be good. So here you can see it's an inverse, right? So it means I want to set all of my weights really big, okay? I'm gonna sum all of those together, and that's how I'm gonna set my regularization, okay? Now our regularization function doesn't care, right? Because as soon as you have a regularization function, which we can plug in like over here, okay, we just plug it in on this side. This is our sigma h, okay? I can minimize it. So I just need a term that goes over here and I can minimize that, okay? But the problem here is when we do weight growth, okay, this case here, which we are saying that we want our regularization values to be very big, our constants to be very big, it actually usually doesn't work, okay? Because most of the things that we set as features usually don't fluctuate wildly on data points, okay? You can sort of make sense of that, right? It could be that there is actual target functions that are really wavy, but the chances of getting them are very small, okay? And so that's why weight growth doesn't work well as a strategy for regularization, okay? So just cross this out, that's no good. Okay, so we don't usually set something like that, but we'll try these two other things, okay? One is that we constrain all of the weights, and we want to penalize large weights a lot more by using a square, okay? The other thing we can do is say something like this, which is the same, but we have a coefficient in the front, okay? So you can see what that's doing as well. That's saying, I want a low order fit. I'm gonna allow you to set a larger parameter value for small coefficients, but not for big ones, right? So if I have x squared, x cubed, x to the 10th, those type of values, those coefficients in front of them, I'm going to set to small numbers, okay? Now here, those coefficients are for x's to take into a certain power, right? So it's not for, let's say, the 10th feature in the vector, okay? It's basically saying that when we take the square or the cube of a particular feature, or a set of features, that we're using another coefficient for that. So this also turns out to be a fairly good idea too, okay, if we want to disallow that, okay? But the standard one that we use is just to say, I just want to constrain most of the coefficient values to be a low number. I don't care whether it's the one on the bias term or the one on the x1 or the slope term or any other one, okay? So hopefully that makes sense to you. All right, so let me go on. Okay, so when we do that, you can see how we might get better values, all right? So when we talk about the bias variance, we talked about stochastic noise and deterministic noise, and we can see how to minimize the values of of error that we get by trying different amounts of regularization, okay? So here on the x-axis here, we can see the amount of regularization that's optimal. That's where the points are, right? So when we have larger amounts of noise, stochastic noise, right? So the green is 0.25, the red one is 0.5, no noise in this case. Then we can change the amount of regularization that we have. So the optimum amount of regularization for some function when we don't have any noise, okay, might be actually to don't do any regularization at all if it's not noisy, okay? So we have a clean target function, there is no noise, no need to use any medicine, okay? But as our target values get more and more fuzzy, we have more measurement error, okay, because our x's are not exactly where they're supposed to be, then it helps to put a little bit of constraint. We put brakes on our hypothesis set. We constrain the hypothesis set a little bit so that we don't get all those wild cases of hypotheses that are going to have wildly varying errors, okay? So of course, as we increase the noise, the amount of regularization that we want to apply, it gets higher and higher, okay? And so this is true. As you can see, the left graph and the right graph look almost identical because again, we don't actually know where the noise comes from. It could be stochastic noise, meaning, you know, just measurement error, or it could be deterministic noise, okay? So deterministic noise actually has two forms, right? But in any case, what we could say is if we have either, in this case, a target complexity, meaning the target function has gotten more complex, okay? The data points that we sample are going to be more subject to distributional properties of having more variance, then we want to have more regularization, okay? So we have a polynomial function that's of order 100, order 30, or order 15. As we decrease the target complexity, the amount of regularization that we need is going to be correspondingly lower, okay? So that's the idea behind that, okay? So, you know, basically what we want to do is try to find not only the perfect hypothesis, right? Because we said in our script H, we want to do that. Okay, so Li Shua asked, but won't decreasing our model complexity increase the bias error? Okay, yes. So decreasing our model complexity, okay, here, means in this case on the right graph is about the target complexity of the target function. So as our target function gets more complex, that means when we sample, there will be more varied data, okay? And that means we can get wilder curves. So we want to apply more regularization to constrain what our weights go to, okay? When our deterministic noise can also go up in the other direction, okay? The other direction is when we have a fixed target function, okay? So let's say our target function is of class H15, okay? 15th order polynomial. And then I don't use a polynomial class in my hypothesis class that is able to model it. So for example, my deterministic noise will go up when I lower my capacity, right? So when I use, let's say H2 or from H10 to H2, I will have more noise because I cannot fit the target function as well, okay? So I hope that answers it. It can go in both directions, okay? It could be that your target complexity increases, so there's a larger gap between the actual function that you're using for your hypothesis, okay, and a target function, okay? Or it can go the other way. I have a fixed target function and I lower the capacity, right? I lower the capacity to fit the target because my hypothesis class is too simple, okay? So that's another way. Okay, now this is in the case where we have enough data points. So as you may have heard in your tutorial, these two cases I'm presenting you are in the case where we have enough points to try to estimate the target function well. Okay, when we don't have enough points, then still we have the problem that if we use a increased hypothesis class, let's say H10 versus H2, H10 can overfit compared to H2, right? Even though we have a more powerful hypothesis class. And that is because the H10 has a better capacity to fit the data, right? And the data can fit the variations of the data set in particular, the sample that you picked out for the data set, right? This is the variance problem, right? So when the variance happens a lot, then our deterministic noise will also rise, okay? So that's why having this part of the classifier choice is also very important, okay? So I hope that's clear to you. Okay, so we have to search for H, right, which is our hypothesis class. We have to search within H in many cases for regularization. So we want to constrain the whole set of possible universe of weights to a reasonable set, okay? So when we choose H, actually we are making a hard decision, right? We are choosing H to say only linear classifiers or only KNN hypotheses or only conjunctive hypotheses. I don't have any way of saying what within that H is particularly good. It's a hard constraint, okay? So you can think of it like this, right? I have an oval, okay? And that's my H. Whatever I decide there is what I'm going to use, okay? So if I pick a different H, it will be a different oval. It will be some other form of hypothesis. It may overlap with one hypothesis versus another, okay? But when we use a regularizer, what we're saying is that within this oval, okay, there are some solutions that are more likely than others, okay? So for example, maybe I say the ones closer to the origin or things inside the middle are more likely, and that ones that are farther away, if I could make this into a, a shaded figure, so from the inside is more blue and the outside is less blue, then maybe that would be an example of a regularizer, to say that instead of putting a hard constraint, I'm putting a soft constraint. You still allow me to set things that are fairly wild, but I have to do that in some way that proves that the rest of the weights are set to 0, okay? So the guiding principle behind this is, again, that we want a smoother or simpler hypothesis, right? Because we don't want all the waves in our hypothesis class, okay? And we're going to sacrifice a little bit of our modeling capability, which is our bias, hopefully for large improvements on the variance, because when we constrain the set of weights, we're not going to be subject as much to the particular pick of our data set, okay? So that's all good. So as a summary, like we said already, basically we are choosing a regularizer, this function, or sigma h, whatever it could be. It could be, again, a lower order fit or weight decay, all of those two that we saw, okay? We're gonna add that as an auxiliary loss function to come up with something we called augmented error, okay? So this augmented error, as we showed you on the math slide, can be also fit in the normal equation. It can be one-step learning. You just need to do a matrix inverse to get the amount, okay? So how do we choose which dose? Like we said in the validation part of the lecture, we can do it by validation, okay? So now that we know about validation, we can also take it up one level further. We can do cross-validation. So cross-validation is trying to solve this problem, okay? We have test error, which we really want to know, okay? So that we can tell our employer, okay, you got our classifier and it will perform in this range of performance, okay? And we have some test error that we can get from validation. And this is going to be approximately true when our amount of validation points is small, okay? Because we know this amount is correct, okay? But our actual validation cost is going to be a good approximation when our K is big, okay? So did you follow this? This part is the difference between using the actual classifier that we would learn over the entire training data set, okay? And the classifier we would use using only the points that are used not for validation, okay? So this is our H minus. So we cut out some points and we didn't use those for training, but but we can use them to accurately estimate our test output on this hypothesis that's trained only over a subset of the entire data, okay? So that's the first part, okay? Then the second part is, how well is the validation cost matching the test cost, right? And we want these two to be true, and we can only do that when K is big, right? If we have a large validation set, these two values will be approximately the same as each other, which is what we saw on the pre-lecture last slide where we saw the two curves going up, okay? So we want both of these things to be true so that we can use validation error as a estimate of the actual test error, okay? The way we do that is really simple, okay? What we're going to do is carry out multiple validation experiments, right? We're actually going to do this idea of leave one out cross-validation, okay? That means at the beginning of the pre-lecture, we said let's estimate the amount of error that we have on our classifier using a single point, right? Because actually that means I get all n-1 points, just 1 point we left out. And so the classifier I get is going to be almost the best that we can do, okay? Almost the best, all right? So when we do that, we have basically a really good handle on our performance, but our estimate of our actual error is not good, right? It's either going to be 100% accurate or off by 100% if we're talking about classification, right? Because we only got 1 point, all right? So what we're going to do is we're going to say, well, we could rotate this point. It doesn't have to be the last point in the data set. It could be the first point. It could be the second point. It could be all of the m points. So that's what I'm going to do, okay? So I'm going to create a data set, okay, which is going to be called my cross-validation data set. It's particular to that particular point. So that cross-validation data set, I have m of these. It just strikes out 1 point, okay? So I use this 1 point to get a validation cost, okay? That's my estimate of the error. And then I'm gonna average all of these together to get my actual cross-validation estimate of cost, okay? So of course, there will be a caveat, right? Because most of the hypotheses that I've come up with will be highly correlated. If you see the S3M, again, the S3M, we say, if you take out some data points that aren't on the support vector, they don't matter, right? So some of these hypotheses might be identical. They might be very similar to each other. And so, they'll be very close to each other. All right. Okay, so then we can get an idea of what's going to happen, right? So when we try to do this, we're going to learn a classifier, H minus CV, and then I'm going to have all of these averaged together, right? And the cross-validation cost will be the average of all of these cross-validation components, right? Because I'm getting 1 point to estimate the cross-validation error, okay, for that single point that I left out, okay? So I'm pretty much using all m examples, right, for K, because I'm getting a set of all of these for training and for testing. So it's like the best of both worlds, right? Okay, so how you can imagine this is, let's say I have a data set of 3 points, okay, and I'm trying to regress a line through them. Okay, so I'm just gonna leave out any one of these points. Okay, so I leave out the first one, I leave out the last one, I leave out the one in the middle, and I regress a line, right? So you can see how bad it is. So I'm gonna average the cost in this regression case of J1, J2, and J3, and that is gonna be my leave one out error. Okay, that's my estimate of the test cost, okay? When I actually run regression, I'm gonna use all 3 of these, and I'm gonna end up regressing a line that goes right in the middle there, okay? Like this, right? Maybe something like that, okay? But of course, when I do your estimates of the test error, I'm just basically taking the average of these 3 red dotted line segments. Okay, so you can see that doing this allows us, even in this simple case, to validate again that in this particular data set, that having 3 points is insufficient, right? Insufficient for getting good values for an H1 classifier. Here, when you have 3 data points, even using an H0 classifier, which doesn't have slope, just intercept, is still usually better, okay? So for this data set, we can show that the constant model is a better fit. Okay, so this is what we do. We do k-fold cross-validation. It's quite expensive because it basically means on training many times, okay, k times, okay? But we leave out a different set of the data in our training, original total training data, right? This entire pie is our training data. We just take out one part of it. We save that for our test estimates, which is called our validation error, right? And we rotate it around, okay? So we can do that. So instead of using leave one out, because if we have a very large M, that could be expensive. So we use k-fold, okay? So again, the k here is sort of sensitive, right? If you have a really large data set, even doing k-fold cross-validation isn't feasible, right? Sometimes we can only run through the data once and we have no choice, okay? So we often decide which amount of folds we're gonna do based on the size of M. How big is the M that we have? How much time or carbon can we use to train a classifier, okay? So we can do this cross-validation multiple times. So we have all of these different classifiers here. We train them on different classifiers, and within each of these lines, okay, where we have a particular model like an SVM or a linear regressor, we can use cross-validation for each of these, okay? All right. So it's nice in some ways. We can get a better handle on our test efficiency, test estimate. But of course, there's an efficiency factor in the sense that we have to spend more time training. Okay. So yeah, I think the last thing I wanted to cover with you is this part here on regularizing LP norms. So you know about the norms that we have for geometry. Okay, so basically here we have different norm values that we have. So we have the L1 norm, which basically is what we call, you know, just differences on a single dimension at once, okay? So we can think of L1 as Manhattan or taxi cab distance in the city of Manhattan because we have a grid. So here, each of the dimensions is separately calculated. So you can see that for each of these points, okay, this point to here, from this bottom left to the bottom right, each of these distance values will be the same, okay, because it requires going up and down, up and down, up and down, or all the way up and then to the right, okay? And so the L1 distance is the same in all of these cases, okay? In L2 distance, right, we're calculating a Euclidean distance. So in L2, we wouldn't be calculating either of these, any of these lines except for the green line here, right? This is a straight line distance from this point to this point, okay? And we can generalize this. So this formula that we saw up here, okay, gets generalized depending on the power P, okay? So when we generalize this, we can figure out that this regularization norm will change, okay? So when we think about L1 regularization, okay, we get a polyhedral that looks a little bit like this, okay? So if you can follow with me what I mean by that, let me see, did I have another slide for that? Yes, I do, okay. Is to say when we use L1 and we use regularization, we set a budget, okay? We set a budget that says, you know, you can use up to 5 units of weight, okay? 5 units of weight for any of the coefficients, okay? So I could set all 5 units on my X, on my theta 1, okay? This should say theta, okay? Or I could use all of my units for theta 0, okay? It doesn't matter. And I can use any combination of up to 5, but if I trade off some amount of weight for X1 and I use it for X0, it's going to define this line here, right? So basically this line has to sum to 5, right? The weights have to sum to 5, okay? So you can see why this encourages sparse solutions, okay? Because in order for me to set and tell you that X1 is important, okay, I'm gonna have to put some of the other weights low, okay? And what happens is when I try to find an optimal solution, okay, an optimal solution to regularization, I'm going to have most of these types of cost functions, if they're smooth and make an oval like the heat map that we saw earlier, the point of first contact on my budget will be an edge or a vertex. So here it runs into a vertex, okay? So this means I'm gonna use all of my weights for X0. Okay, I'm gonna set all of my budget, all of my 5 to X0, okay? And I'm not gonna use X1 at all, okay? X1 is set to 0 because I'm on this vertical, okay? So this is why we say that L1 regularization, when we're using L1 regularizer, encourages sparse solutions, right? And it does feature selection, because then by the geometry of the regularizer, when we look at how the cost function bumps into the budget, it's often going to bump into an edge, a vertex, or a face, right? Depending on what type of geometry it is, okay? On the other hand, when we think about L2, okay? L2 regularization, as we said, is Euclidean distance, right? So when I introduced that weight ball earlier, you know, when we had the pre-lecture with the heat map, you know, I drew a circle, a red circle, right? That circle is a hypersphere, right, in higher dimensions. So it looks a little bit like this one here, right? Okay, so you can understand where this is coming from, okay? So I have basically a Euclidean distance is going to admit a hypersphere for the space, okay? So when I have a hypersphere, you can see what's going to happen. These ovals, again, this is the same cost function, is going to bump into this hypersphere at some point, okay? It's much, much more likely it bumps into this sphere at a place where all of the values of the features are non-zero. They're small, but they're not zero, okay? So it's different from the geometry of this one, right? If I look at this, no matter where I put this oval, okay, I change the orientation and I change how it expands, it's very likely to run into an edge or a vertex, okay? And that has a chance of setting some values to 0. Whereas in the case of something like an L2 regularizer, it's basically saying that the best solution is going to be a combination, a low order combination of almost every coefficient, okay? So this is the case when I just have two weights, you know, a theta 1 and a theta 0 here, but you can generalize that, right? So if you look at the LP norms here, you can get a sample idea. So P of 1 equals this polyhedral, P of 2 is a hypersphere. When we allow the budget to take any amount, but we allow the exponent to be any number, okay, a maximum of infinity, then it's going to look like a square, okay? So a cube, a hypercube, okay? So you can get an idea of how that works, okay? In 3 equally weighted dimensions for x1, x2, x3, and I have theta 1, theta 2, and theta 3, then I would have these configurations for what the budget C looks like in that theta space, okay? So it's a nice way to understand why L1 actually encourages sparse solutions. It's a property that falls out naturally from the geometry. So I think that's extremely cool. Okay, so with that, I'm gonna stop my screen share. Again, I apologize for all of the problems with my home connection. So we can talk about other parts. So can you go through the derivation of augmented error? From what I got, it seems like we are doing a derivation with respect to theta transpose. So we were doing a partial derivative against theta, right? So when we do the partial derivative against theta, the terms will naturally fall out that we have just a single part that's dependent on the lambda function times an identity, right? So let's see whether we can raise that up again. And then hopefully that will answer that. Okay, hold on a second here. Yeah, okay. Right, so let's just take a look at this. I have to share the screen. Let me do it again. Okay, so I think you can see the screen again. So again, what we're doing is we're taking in this first step, okay, we have a hard constraint. We're saying subject to this constraint that it must be falling within the polygon that I've defined as the budget, centered at 0, right? Because we, again, our weights are saying they have to be a maximum amount. Okay, so 0 is always the origin here. Okay, so we are just changing it to a soft constraint. Okay, so we don't make a hard constraint. We just say what we're going to do is we're going to add this constraint as an auxiliary loss. Okay, and we're going to allow the constraints to settle it for us. Okay, so we want to minimize our training error, but also minimize this part, right? And so this is a lambda divided through by the point m, right? The number of points, okay? So when we multiply this out, we can take the m in the front, so that's no problem. And we have our training error, which is illustrated in this part. And we have our penalty for regularization, which is just going to be the lambda times the actual weight norm, right? The norm of the weight. So this is the L2, the norm of the weight, right? The weight vector times itself, okay? Then again, we're gonna take the derivative of this augmented error. We're gonna set it equal to 0, right? So this is a vector of 0. So we're gonna set all of the components, our theta 1, our theta 2, all of these to 0, okay? The partial derivatives of 0 and solve them, right? So then what we're going to get out is when we multiply these out, we're going to get this value here, right? Okay, so how do we do that? What we saw is when we have this square here, right? We're going to end up with one factor of theta times lambda, that's this one here, okay? And we're going to end up with one factor of theta by itself that goes out, okay? And then we have the rest of these terms over here, which is as normal. So we have this part on this side, okay? So hopefully you're clear of this because we have a square, right? We have a square here, we have two parts that come out, okay? Then what we're going to do is we're just going to factor. We can multiply these together, right? So we get our x transpose x, right? And we're gonna carry the theta out as a norm, okay? And then our y, again, we're taking the derivative, but it doesn't have a part there. So then we only get the minus x transpose y as an out term, okay? And this part here, again, we just carry it over. So we'll get a lambda function, just a lambda constant, sorry, it's a scalar, right? And we'll have the identity matrix to make it work in the vector representation, okay? So once we have that, we are done. Basically, we end up with just the same thing as before, right? We can solve for this by just putting this over. So then we have basically just this term, right? We just need to add this matrix of values, which is just the lambda function times identity. So it's the same regularization constant striped all the way on the diagonal. And it's just affecting all of the setting of the coefficients for our regularization, okay? So that's a nice side effect, right? That we don't have to do a lot of extra for that. Okay, so let me see. I think, let me not save that. Okay, do we have any other questions that you guys would like to know? Then I will take your questions now. So you can do it by chat, or you can put it on the Ask Me Anything. So hopefully that's clear for you. Okay, with that, I think we are done. So I thank you for joining our help session this afternoon, and we've done our lecture recap. So we'll see you a little bit early, hopefully on Monday next week, and I hope you enjoy your recess week. Okay, take care, everyone. Okay, you're most welcome. I always like to interact with students, even if I can't see you. Again, I apologize for the problems with the connection. Yeah, if you're not sure, you can always ask, okay? Ask in email or ask on the forum. We'll try our best to answer you, especially if you have your concerns. Cheers, everyone.